First of all, I thank the organizers for giving me an opportunity of this talk. This talk is concerned with the structure of radially symmetric positive stationary solution for a competition-diffusion system. In 1979, Shigeada-Kawasaki and Teramoto proposed this kind of reaction diffusion system, which described the dynamics of population densities for competing species. W and Z are population density, alpha and beta are non-negative constant, and the other, for example, dW, dZ, A, B, and C are positive constant. Omega is a bounded domain Rn. L is a space dimension, but we assume this L is a real valued parameter. Omega is a smooth boundary in Rn with smooth boundary, and this is outward normal derivative on the boundary. As you know, there are many studies so far. I don't mention the detail. We use this change of variable here. This change of variable is a bijective map from the first quadrant to itself. By using this change of variable, we can rewrite the SKT model as this kind of reaction diffusion system. Capital phi ij, F0 and G0 are phi ij, F0 and G0 are determined by the original system. We define this variable like this, then the stationary problem is like this. F is determined by the original function, or original SKT model, but this expression is very complex for me, so that I cannot treat this system directly. So I take strategy as follows. First step is we assume some assumption, for example, two assumptions on this nonlinear term, and then we investigate this system, stationary problem, and then establish the structure of stationary solutions. Second step is we feed back the obtained result into this original SKT model. In this talk, we take omega is a ball with center origin and radius pi. And we consider structure of radially symmetric positive solutions for the stationary problem. Stationary problem is before here. These solutions satisfies this stationary problem. This operator K comes from the minus Laplacian operator with radially symmetric property. We often use this order relation. this is the usual order relation. And L is a space dimension, but L is a space dimension, then L is a positive integer. But in this talk, we regard L as a real valued parameter satisfying L bigger than 1. We assume that we impose the assumption, two assumptions, A1 and A2, on the nonlinear term. This assumption will be mentioned later, immediately. When alpha and beta are small, the SKT model nonlinear term obtained from the SKT model satisfies these assumptions. This is a picture of the set of stationary solutions. For example, this is a set of stationary problem for reaction diffusion system. This is for competition-diffusion system. The classical Rotokar-Volterra competition-diffusion system is a competition-diffusion system with nonlinearity of second order. SKT model connects classical Rotokar-Volterra competition system and usual reaction diffusion system by using the parameter alpha and beta. So our stationary problem is here, inside of competition diffusion system. We impose two assumptions on the nonlinear term. This is the first assumption. First assumption is follows. If there is a positive and there exists positive delta such that this inequality holds for any u in the first quadrant. This assumption, I would like to remark, this assumption implies that the stationary problem becomes a weakly coupled elliptic system with respect to this relation. This relation is here, this relation. That is, the comparison principle holds for our stationary problem with respect to this order relation. Second assumption is as follows. There exists positive constant alpha u and alpha v such that these inequality holds true. And this equation has a unique positive solution E hat. This condition means that this solution is unstable equilibrium point of this ODE. We set these 2 points and this region. I would like to remark this equation on the first quadrant has no solution other than origin E minus here, E plus here, E hat here. Moreover, E minus and E plus are stable equilibrium points of this ODE. This is a picture of the zero level curves for U0 and G0.
Okay, so you're in the bistable case.
Yes, bistable case. This is an unstable equilibrium point. This is a typical example when the minimum B and C is bigger than 1. This nonlinearity satisfies the assumptions A1 and A2. This is a nonlinear term of classical Lotka-Volterra competition model. Let us consider the local structure near this point. Let lambda k and phi k be an eigenvalue and its corresponding eigenfunction of the operator k, that is a minus Laplacian operator. Without loss generality, we may assume this condition holds for each k. This result is well known. First one is lambda 0 is equal to 0, and lambda k is increasing in k for each L. And the eigenfunction can be represented as this form. L is equal to 1. The eigenvalue is a cosine function. L is bigger than 1. Eigenfunction is a Bessel function. We assume this assumption, this condition. Then, usual bifurcation theory, we obtain the following result. For each L, there exists a branch of non-constant stationary positive solutions for the stationary problem, bifurcating from constant solution we had at this point. This is a numerical example. Numerical example for the case where the nonlinear term is like this and n is equal to 1.1. When the intercompetition rates B and C are comparatively small, then secondary bifurcation never occurs. But when B and C are comparatively large, the secondary bifurcation here and here occurs. They are of saddle node type bifurcation. So I would like to calculate local structure. This is an assumption. Then these two equations has non-trivial solution B and B star. This operator has simple eigenvalue and its corresponding eigenfunction is this function. This function is an eigenfunction of kappa, this operator with respect to lambda k. We substitute this estimate into the stationary problem, and then we obtain this estimate. This function is a bilinear map obtained from the second derivative of f of u at the constant solution E hat. So we define capital phi in this way. M is a power. Then from the Fredholm alternative, we have this formula. This formula determines the bifurcation direction of direction of the bifurcation. By this definition, we have two facts. One is phi LK2 is also positive for any L and K. And when L is equal to 1, phi K is a cosine function, so this value is equal to 0 for any K. When L is equal to 1, so this term is equal to 0. Then this first order term is equal to 0. So this term is equal to 0. Then to determine the local structure, we need to investigate this second order term. When L is bigger than 1, so this value is unknown. So we need to study this value. We employ not only mathematical method, but also the numerical verification method, such as the interval arithmetic built in the Mathematica. And then we obtain this result. This is one of main result of this talk. Phi LK3 is positive for any L and K. These blue colored terms, this are positive. So to determine the local structure, we study this value. We use this nonlinear term. We calculate numerically this value. This value is equal to 0 on this surface. Okay. This is a b-axis. This is a c-axis. This is a d-axis. This value is equal to 0 on this surface. This is positive for this in the back of this surface here. And this value is negative in the front of this surface here. I would like to remark the direction of branch does not depend on the parameter L and K for this nonlinear term f of u. So this is this is my problem. Our problem. X is a set of C2 class functions which are positive for any R in this interval. Let Bk be the branch of solution for our stationary problem, bifurcating from the constant solution E hat at this point. For example, Bk branch is like this. This is an image. Secondary bifurcation. It is possible that secondary bifurcation occurs, but number of the bifurcation points are known. This is our problem. When k is not equal to m, does the Bk branch have the same structure as the Bm branch? this branch and this branch are same or not? My answer is yes. We obtain this theorem. Let k and m be an arbitrary positive integer, and let this function, these points be arbitrary. If the first element at r equal to 0, and u2 at r equal to 0 is this value is equal to this value, or this value is equal to this value, then this relation holds true for any r in half line. From this theorem, we find this result. This is an original branch, and this is a new branch. This is a bifurcation point. This kind of bifurcation never occurred. So the secondary bifurcation is of the saddle node type, even if it occurs. This is like this. This type does not occur. So this is a bifurcation point here. So we rotate it 90 degrees. So this solution branch is this solution branch is parameterized by P, this line. But the number of saddle node bifurcation points is unknown. This figure shows 3 saddle node points, but this is unknown. Let me show the key points of the proof until the time is up. So at first, I explained my idea of the proof for using a reaction diffusion equation. A is we assume A is positive and smaller than 1 second. So, and we consider this reaction diffusion equation. This is a U axis and this is a U prime axis. When L is equal to 1, there is a homoclinic orbit like this, and when L is bigger than 1, we have this trajectory. This solution is oscillatory and tends to constant as R tends to infinity due to the effect of damping term. We adjust space variable, then this solution corresponds to a element of B1 branch. This solution correspond to a solution B2 branch. So each solution of the BK branch represented as this one function. So I think that the structure of BK is probably same as the B1 branch for any K. Second idea is here. Let me consider this cases. That is a case where there exists tau such that U tau is equal to 0. We obtain this purple trajectory. The initial data are a little bit small, so we obtain this blue colored trajectory. So this blue colored trajectory corresponds to a monotone solution for the reaction diffusion equation. More decreasing, more small, then we obtain green curve, green trajectory. This corresponds to the solution, this kind of solution. We use this technique to the competition-diffusion system. Let U0 be an arbitrary positive solution for the stationary problem for epsilon equal to epsilon 0. This function is a solution of this stretched stationary problem with this initial data. This operator is defined in this way. This operator means the element-wise multiplication. So we can classify this function into the these three cases. One is this function is positive and inside this region. Second case is this function is positive and unbounded. This case is there exists some point and some point such that this solution intersect U-axis and V-axis. To prove the theorem, we show that the case C2 and C3 never occurs, and the stretched stationary problem with this initial condition has a unique bounded positive solution. To show the former part, this part, we assume these two cases, C1 or C2 occurs, and then we derive a contradiction. This is a first lemma. Every solution of the stretched stationary problem satisfies this inequality. This inequality means this solution does not approach the origin. This is the origin. We state for the reaction diffusion system, initial data changed. So this is initial data changed using by a parameter P. So this function is a solution of stretched stationary problem with this initial condition. We denote by P minus and P plus. We define P hat tail and this function. This function is positive for any R in the half line. This is the second lemma. This function satisfies the following. So the lemma 2 is obtained from the comparison principle and the continuity of solutions for the stretched stationary problem with respect to initial data. So P tends to P hat 0. So the solution converges, approaches boundary and exterior of domain D. So these functions are monotone in the neighborhood of R equal to infinity. Then by using this spatial profile, we apply the method of moving plane to this function, and then we obtain the following. This lemma says that this function is monotone for any R in the half line. Let us consider the case C2 because case C3 will be proved in the similar manner. So this case implies P plus is negative. We calculate these values. So this inequality falls for any R in the neighborhood R is equal to 0. We set this function in this way. So the boundary condition at R equal to 0, then we have this condition. We calculate this derivative and then use the fact this function and this function are solutions of stretched stationary problem, and then this estimate. So we integrate this inequality and then we obtain this estimate. So this estimate, from this estimate we obtain this contradiction. So this inequality holds true for any R in this interval. At by the boundary condition at R is equal to capital C0, then this value is 0. So we obtain this estimate. This estimate means both elements are same sign. For example, negative. This contradicts the fact of lemma 2. Lemma 2 shows the opposite sign. Hence, we derive a contradiction, so the case 2 does not occur. So we can similarly prove that case 3 does not occur. So we see this function is positive and bounded for any R in the half line. Okay. This is a proof of the farmer part, but I cannot. I have enough time to the uniqueness part. This is a uniqueness part. I cannot explain the uniqueness part. So this part is precisely calculate. We precisely calculate this function, calculate this function, and we obtain precise estimate. Then we have a uniqueness theorem. So this is a summary of this talk. The structure of the BK branch is the same as the B1 branch for any K. The structure, so we only study B1 branch, but the structure of B1 branch is still open problem. Thank you for your attention.